Welcome back. In this lecture, I want to go into a little bit more detail about using the numerical solvers. So recall that the Brain Dynamics Toolbox provides many different types of numerical solvers, or rather I should say MATLAB provides most of these. The ones that are marked here with an asterisk are those that are provided by the toolbox itself. But with all these solvers, the dilemma is which one do you use? And once you've chosen one, how do you adjust the error tolerances to get the best out of them? Now let's start by quickly revising the initial value problem for an ODE. So in this case, we want to find or estimate the exact solution here in the black curve. But we don't know what that solution is, of course. All we know is the initial value y0 and the time t0 of that initial value, and we can use those values, plug those values into our ODE to get the gradient dy dt at that particular point. So once we have that gradient, we can take a fixed step forward in time, apply that gradient to estimate the next value of y in our time series, so y1, and we can just repeat, get y2 and so forth, and that's how we forward integrate or integrate a initial value problem forwards in time. Now that basic approach that I described corresponds essentially to Euler's method, and it works by approximating the continuous system using these discrete steps, and we can rearrange these terms to get an iterative expression for y of t plus 1 in terms of yt plus the instantaneous value of f times the time step dt, or delta t. Now, contemporary solvers use higher order methods which provide much better accuracy, and they provide much better accuracy because they make multiple evaluations of the function at intermediate steps to get a better estimate of those gradients. In this case, we have a fourth order Runge-Kutta method, which is using 4 evaluations of the function to make the ultimate estimate of y1. Now, without going into details, fourth order methods have an accumulated error of order h to the power 4, where h is the time step, and of course you could extend your fourth order method to a fifth order method, and that would give you an error estimate of order h5, h to the power 5. Now the really cool thing about these methods is that the fourth order and the fifth order methods have interwoven terms. That means that the same expressions used to compute the fifth order are also used to compute the fourth order estimate. So basically, if you're going to compute the fifth order estimate, you essentially get the fourth order estimate for free. Now once you have the two estimates, then you can compute the error between those two estimates. And once you have the error in your hand, then you can use an adaptive step size method. So with the adaptive step size, if your estimated error is larger than you wish to tolerate, then you can reduce, or the solver can automatically reduce the size of that step. If the error is too small, then the solver can automatically increase the size of that step, and that's called a multi-step method. Now in MATLAB, we have 2 error tolerance values or parameters that we use to specify the tolerances for these solvers. One is the absolute tolerance, and that is, as you'd expect, is the absolute value of the difference between these two estimates. And the relative tolerance is the same difference but scaled by the magnitude of the state vector y0. So you can think of the relative tolerance as giving you the or specifying the number of significant digits you want to have in your solution, and the absolute tolerance is the smallest error below which you don't really care about. So with that, let's go see how this works in terms of the toolbox. So let's return to the linear ODE model that we used in the last lecture. We started the same as before. I'll just stick with this because it's simpler. Here's the time series and here's the phase portrait. So in the phase portrait, this is our initial condition, and we spiral into this fixed point here where the green null lines cross. Now the solver tab includes our absolute and relative tolerances that are used to control the adaptive time steps. In this case, we're using the ODE 45 solver, which is the Runge-Kutta 4-5 order algorithm. And here we can see the time steps taken by that adaptive solver. So as the simulation progresses, larger and larger time steps are taken. And we can see the actual time steps taken in the time portrait by selecting the time points menu option. We can do the same in the phase portrait. Phase portrait, time points. Now, let's explore what happens as we change these absolute and relative tolerances. So what I recommend doing is starting with a high tolerance in both fields. 1e minus 10 is plenty high. We'll go back to our time series, and actually I'm going to turn off the time points and take a snapshot of this particular trajectory. It represents our gold standard, if you like, under these very strict tolerances. So time portrait, hold. The hold menu will take a snapshot of that, and it looks like nothing happened, but the snapshot is occluded by the black line. So if we move our parameters a little bit, we can see that green line is our gold standard. Let me put the parameter back to 1, and I'll take a snapshot of the phase portrait also, why not, and restore the time points in both. Okay, now we're ready to go. Let's go back to the solver panel, and what I'm going to do, I'm going to undock the solver panel from the main GUI. There it is, floating in its own window, and just move it down here so we can see the tolerances alongside the time series. Alright, so we have very strict tolerances. Now, let's see what happens as we reduce these relative tolerances down. We start with the relative tolerance, because remember, the relative tolerance is kind of akin to the number of significant digits in our simulation. So we'll start with that. We'll go -9, -8, one e minus 8. Keep dropping it down. So we're loosening the tolerances, accepting more error, and we're just looking to see at what point does the solution start to deviate too much from our gold standard. So if you can see, we go right down to 0.1, well, let's go down all the way to 1. An error tolerance of 1 does quite a poor job of fitting that curve. But if we go 1e minus 2, it's getting better. There's still some poor fits here. Let's go 1e minus 4. or even 1e minus 6. Actually, in general, I find 1e minus 6 is pretty good. That's probably a bit too much. We probably don't need it quite that much in this case. All right, so now we have our relative error tolerances. We can now reduce the absolute tolerance. Now remember, the absolute tolerance represents the smallest error that we don't care about. And if you think about what's happening down here when the solution is converging to that fixed point, you can see it here too in the phase portrait, and the solution is converging to that fixed point. Even though it's too small to see, it never actually converges to the fixed point proper. It just continues to oscillate ever smaller around that fixed point. And we can have a peek at that by sliding the time window to, let's say, 18. Let's just make it 18. We'll slide the time window up to t equals 18. And what I can do now is I can hide those transients by unchecking the transients menu. And now we can see the time starts from 18 up to 20. And if I recalibrate that, I'll fit the data to my available window, and I can see that even down at this very small level, we're still oscillating around that fixed point on our approach. But at this level of detail, we don't need all these fine steps. So this is where we can reduce our absolute error. Let's go 1e minus, well, let's just do it slowly. 1e minus 9, minus 8, 7, 6. Okay, so you can see here that the steps are starting to deviate from the gold standard, but they are, remember, we're talking very small values here, very small absolute values. So if we go back to the full time span, recalibrate so we can see the whole thing, we can see even though there was, we can see errors in the small scale solution down towards the end of the simulation. The errors at the transient part or the early part of the simulation are pretty good. So I would say that's a fairly good choice of relative and absolute tolerances for this particular simulation. And if we come down to the solver bar down the bottom, we can see that this particular solution used 80 steps, which isn't bad. There was one failed step. The failed step means that the auto stepper stepped a bit too far and had to pare it back a bit. There was 487 function evaluations in those 80 steps. The number of evolutions, that's nothing to do with the solver per se, that's the number of times that the solver is run with the evolve button on. I can't remember if I described the evolve button or not, but the evolve button, every time you run a solution with the evolve button enabled, the final or the initial conditions of the next run are replaced by the final conditions of the current run. So the initial conditions get evolved. So these will change according to whatever the final solution is. And that allows you to run long simulations in small batches. But anyway, that's something else. The solver CPU time is something to keep an eye on as well. We use 0.01 seconds for this particular computation, but if we, let's say we ramped everything back up to our gold standard, what would that cost us in time and computations? That would cost us 765 steps, 4,615 function evaluations, and 0.04 seconds. So you can see it is worthwhile tweaking the error tolerances to get the best performance out of your solver. Okay, I will just put that back to -5 and this back to -6, and I can close that window down. Now, I haven't talked about solver selection yet. So there are only 3 solvers available in this particular model. I can't quite remember why I only have 3 solvers here. Most models have at least 6 or 7 choices of solvers, but in this case we've only got 3. ODE 45, ODE 23, both of which are provided with MATLAB, and ODE Oil for Euler. Now this is a fixed step method. So if we switch to ODE Oil, we'll see a very poor, I'll calibrate this so we can see the whole thing. We'll see a very poor result where we have an unstable solution which starts to fly off to infinity. And the reason is that the time step we're using is too much. I should have kept that solver panel, so let's bring it back. Solver panel. The time step here is 1 time unit, and that's specified here by the step edit box in the GUI. So if I change this to 0.1, so you'll see my time steps drop down to 0.1. I'll start getting a slightly more sensible solution. I'll recalibrate so I can see it. Okay, so remember the green is the gold standard and the black is what we are currently computing. Still not a very good solution. 0.01 step size. There we see we've converged fairly well to the gold standard there, just by adjusting that step size. So the Euler solver is a fixed step size solver. It doesn't automatically adjust the step sizes. Just calibrate those again so we can see them. It does not automatically adjust those step sizes. It just takes a fixed step each time, and the size of that step is entirely up to you. What else did I want to say about that? I can't remember. So the Euler. As for the other solvers, there is some good documentation in MATLAB called under Choose an ODE Solver. Choose an ODE Solver. That's the one. This is worth a read. This help page gives some overview of the different types of ODE solvers. I wouldn't read it too deeply. I think you could basically skip to the section on basic solver selection, as this gives some good practical advice on choosing the right solver for the job. Now, in general, you always start with ODE 45. That is a general purpose solver that generally does a pretty good job. Now, if you have a stiff system, now a stiff system is one that has lots of tight turns in it. A stiff system can be done better with ODE 23 or ODE 113. In fact, also these other solvers that have the S subscript at the end are all designed for stiff solvers. So it's worth a bit of a read on following this, but I wouldn't spend too much time on it, quite frankly, because the best way is just trial and error. You start with ODE 45, you compare that to ODE 23 or the other solvers that you think might work for you, and you see which one works the best. And in practice, that's how everyone does it. So that's solver selection and error tolerance configuration. I think I've covered everything there for you. I will stop at this point and let you have a play.